Good morning, evening, afternoon, or whenever you're watching this, and welcome to your first lecture of Math 104, College Algebra and Trig. So before we get started, I do just want to say two quick things. One, I apologize in advance. My handwriting is notoriously bad, and unfortunately, my tablet will not arrive here until Friday, which means that this lecture, and hopefully only this lecture, will be done using my mouse. Okay, so just mouse on laptop. Just bear with me. It's not going to look too pretty, but at the very least, it will be bearable. Secondly, I want to say that this is being taken, or I'm sorry, recorded in one shot, no editing. So if there are problems or if I said something incorrectly, then what we'll do is I'll just make an announcement, probably on Blackboard, hypothetically just saying something like at timestamp 3:32 in lecture 1, I incorrectly said XYZ when I meant to say ABC. So that's how we'll treat those one-off cases. But again, I don't anticipate that things like that are going to happen too often. I just wanted to let you know of, the current status of how these are being recorded, and going forward, it should get better, seeing as how I'll have my tablet. So with that being said, we can go ahead and we can actually get started with the lecture. So everybody here should be basically familiar with numbers. And when I say numbers, more than likely what comes to your mind are probably whole numbers. So, 1, 2, 3. You might even think of negative numbers, -8, -9, so on and so forth. What you also probably think of is when I say operations, you probably think of the common operations that you're used to, right? So you have your addition, your subtraction, you have your multiplication, and your division. Before we move forward, I also just want to note that this is kind of a bad habit coming from high school or even before that regarding multiplication. So I've seen on like the prelim exam, for example, people were doing things like this. So they meant to say 2 times 3, right? And in the past, you probably used this x to denote multiplication, right? Please do not do this anymore, okay? Do not use the x to denote multiplication. The reason is because we're going to be working with variables where most of the time it's going to involve an x. And I just don't want you guys getting confused, and I also don't want myself getting confused if you meant to, use the variable and, it appeared like multiplication, so on and so forth. So the two acceptable ways to denote multiplication, first is this. So you have one or even both numbers inside of parentheses. This is totally fine. And then the other way is just with a little dot. So if you do this, this is totally acceptable, and I'll know, obviously it's 6, right? Okay, so with that being said, I also want to kind of discuss before we really get going the order of operations, right? So I saw a little bit of confusion on the preliminary exam, and I just wanted to touch on this. So what you guys may or may not remember is PEMDAS, right? So what PEMDAS is just an acronym for basically all the operations or most of the operations that we're going to be utilizing in this class. So it goes in order from parentheses to exponent, multiplication and division, and then finally addition and subtraction. What do I mean by this? Well, let's take, for example, a case where we have 3 minus 2, sorry about that, times 4, right? Okay, so reading this from left to right, as if you were reading a language, you might be inclined to say, okay, well, I'm just going to subtract first, so 3 minus 2 would give me 1, right? And then 1 times 4, and then that just leaves us with 4, right? This would be incorrect. The reason is because we have to go by order of operations. So what takes precedence here? Well, we have two different operators. We have subtraction and we have multiplication. So what we really have to do is we have to say, okay, well, multiplication has to come first. So instead of doing the subtraction first, we have to do, okay, 2 times 4 is 8. we still have the subtraction, right? We never touched this part. We knew that it was a -2 times a 4, so we know that this is a -8. So it's 3 minus 8, and then we know that that is -5. Not the greatest looking 5, but again, bear with me here, okay? So order of operations, pretty important. Hopefully, I don't need to touch on this too much, but why don't we do just one more example, just so we really, kind of hammer down the point here, right? Okay, so say we have parentheses here, and in parentheses we have 3 times 6, and this is going to be subtracting 2 times, why don't we just say 1 plus 1. Okay. So we have a lot going on here, right? We have multiplication, we have parentheses, we have subtraction. Okay. So what are we going to do here? Feel free to pause the video here. You guys can go ahead and give this a shot. Just give it a couple seconds. It should be fairly easy, given just following the rules of PEMDAS. So I'll give you guys a couple seconds. Okay, so hopefully all of you guys got it. So the idea here is we have to start with parentheses first, right? So we have 2 different parentheses. You can start with either of them, doesn't matter. So we'll start with what's inside this one, right? We have 3 times 6 inside of the parentheses. So 3 times 6 gives us 18. We haven't really done anything with the -2 yet, right? So this is, 3 times 6 minus 2. We haven't done anything with this. So we just bring that down. And now we have the 2 times whatever's going on inside of the parentheses. Now it's 1 plus 1, should be fairly simple. That just gives us 2, right? Okay, so from here, now what do we have left? We have 18, we have a subtraction, and we have another multiplication going on, right? Remember, 2 times 2. This is how we're going to denote multiplication from, going forward. So 2 times 2, that's going to have precedence over the subtraction, right? Multiplication comes before subtraction. So 2 times 2 is 4. And we have the 18 minus 4, and finally that just gives us 14. Okay? So hopefully all of you got that. If, again, this is something that you have trouble with, please just message me on the side. We can definitely go over it in private or during office hours. Okay? So this is just something that I kind of expect all of you guys to understand going forward. Okay, so with all that being said, let's start thinking about numbers in a different way. So again, when I said, think about numbers, you probably thought of them as like one-off things, just, 1, 2, 3. Again, I mentioned there's negative numbers as well, right? And you were probably only thinking about entire numbers, probably not like fractions, right? So the way that we in the math world talk about numbers is generally we talk about them in terms of sets. So what is a set? A set is generally just a collection of things, and those things are called elements. So I'm not really big on definitions, like formal definitions. I'm never going to really test you guys on it, but seeing how this is an online format, I figure I will just write it for you. So a set, you can just think about it as a collection of things or elements. Okay. All right. So we will go ahead and just put this off to the side. Okay. So what kind of sets are there? Well, let's think about just positive numbers, entire numbers first, right? So we have 1, we have 2, 3, and then, so on and so forth, goes on until infinity, right? It just keeps on going. So what we call these are natural numbers, also denoted by kind of like a weird looking N. It's not, it's not really an N, but it is. So this is kind of like the mark that we use for natural numbers. Now, if you add 0 into it, then it's no longer the natural numbers. What it becomes is it's known as whole numbers. And then finally, if you go ahead and you add in the negative numbers, so -1, -2, ... right? And then that goes to negative infinity. What you call that and what you call the whole thing is you call these integers. And integers are going to be defined basically by this like notation as kind of like a z looking thing. Okay, again, not too important for you guys to remember the actual notations. You don't have to really remember the n or the z, but just understand that the way that we classify numbers is by considering them as parts of different sets. So what you can actually take notice of is that the natural numbers, going on from 1 to infinity, is a set, and this is what we call a subset of the integers. When you have a set inside of another set, we call the smaller one a subset. Okay? All right. So why don't we go ahead and clear this off real quick? Okay. Okay, so other definitions that you guys should be kind of aware of. Again, we were talking about numbers. Let's also go ahead and talk about variables. So what is a variable? A variable in general is just something that will represent an unknown value. Most of the time we use letters in English. We use English letters like X, Y. Those are the most common ones that you'll find us using. But again, it could be really anything. For all I care, you could, really draw a picture and it would be totally accurate as long as you use that same picture all the way down, throughout all of your steps. So we have variables. We also have constants. Constants are fixed numbers, usually in combination with a variable, and I'll give an example in just a second. When a constant is multiplied against a variable, it's known as a coefficient instead. Okay, so what do I mean by this? Well, let's go ahead and we'll look at an example. So let's say we have 3x plus 2. Okay, so looking at this, obviously we have the operator, which is addition here. But more than that, according to what I just talked about as far as definitions are concerned, we know that x is going to be our variable. We don't know what x currently is. In fact, because we don't actually have an equation, we have no way of figuring out what x currently is. So x is just a variable just to represent some unknown value. Now we also have the constant, which is right here, and our constant value is going to be 2. And the reason that this is a constant is because there's nothing happening to it. This is just remaining 2. There's no operations going to it that we can really like simplify down. So when it's at its bare bones, when you can't do anything else to it, then you have a constant, and that's 2. And last but not least, our coefficient, which I'll denote with green here, is going to be 3. And the reason that, again, we can make the differentiation between constant and coefficient is that our coefficient is multiplied against the variable. Hopefully that all made sense for you guys. Okay. All right. So moving forward here, we also have 2 other definitions, which, again, I'm not huge on definitions, but they do go over it in your textbook, so it's fairly important to understand. Terms and expressions. So term is just going to be any standalone number, variable, or product of them. So what do I mean by a term? Well, we had, in our previous example, we had 3x plus 2, right? So a term is going to be this guy, and then this guy. So we have 2 terms in this, in what's called an expression. An expression is just going to be a combination of terms, kind of like a sentence is a combination of words, right? Okay. So given all that, let's go ahead and move on to equality and inequality. So we talked about operations, right? We talked about addition, subtraction, multiplication, division. Let's talk about comparing numbers or comparing variables. So if we use an equal sign, right? An equal sign basically means is. So if I say x is equal to 4, that's saying x is 4. X cannot be anything else. X is 4 in this example, and it is no other number, okay? However, we also have other ways to represent numbers, right? We have less than and greater than. So less than and greater than. And these kind of just denote the different sizes in perspective from one side to another. What do I mean by sizes? Well, say we have x is less than 4 in this example. That means that we don't necessarily know what x is, but we do know that x has to be less than this side here. So because this side is 4, we know that x is going to be no bigger than 4. In fact, it won't even be 4. It can get very close to it. It could be 3.9, 3.99, 3.999, so on and so forth, but it'll never be larger than or equal to 4. It could also be obviously negative numbers like -2, -3, so on and so forth, because negative numbers are going to be less than positive numbers. Okay, and then if we just change it around and we just say, okay, well, what if x is greater than 4? Well, that just means that, again, we don't necessarily know what x is, but we do know that with 4 being the comparison here, x has to be bigger than 4. It could be 5, it could be 10, it could be a million. I don't know. We don't know, but we do know that eventually, we landed at the idea that x is bigger than 4 here. Okay. Okay. The last two inequalities that I want to discuss, kind of along the same lines. We have greater than or equal to. So basically, this aligned underneath the greater than just means that it could be 4. We don't know that it's exactly 4, but we know that it could be 4. The difference between the top and the bottom here is that the top one could be 4, whereas x can never be 4 in the bottom example. Okay. Similarly, if we just do it the other way, so the other direction here, x is less than or equal to 4 means that, again, we don't know what x is, but it could include 4. In this example below it, it cannot include 4. So x, like I said, in the bottom example could be 3.9, 3.99, so on and so forth, but it'll never be 4. In the top example, it does have the possibility of being 4. Okay? All right. So let's go ahead and kind of combine everything that we're talking about here. Okay. So why don't we do an example? I want you guys to evaluate the following, okay? So in parentheses, x plus 6 divided by 3. For the record, just before I continue, 2 different ways to denote division. One is the actual division sign, which, you have the 2 dots kind of like over the subtraction. The other way is a fraction, right, where you have like some number over another number, okay? But in this example, I'm just using the division sign. Okay, so we have x plus 6 in parentheses divided by 3 plus x. And this is all under the idea here that x is equal to 3. Okay. So remember what we just discussed. If we have an equal sign, that means x is 3. That means that wherever we see an x in this expression, we can then plug 3 into it. And again, we know that just from purely this part here, right? So what we're going to do is we're going to go ahead and we're going to put x is equal to 3, or we're just going to put 3 in wherever there's an x. So here, and also here, right? And then we're going to change this up and evaluate it from there. So because x is equal to 3, we now have instead 3 plus 6 divided by 3 plus 3. Okay. So now this kind of goes back to what we were discussing before with PEMDAS, right? So we have parentheses, exponent, multiplication and division, and then addition and subtraction. So what do we have in this example? Well, we have parentheses, we have addition, and we have a division, right? So we're just going to go down in order. So first is parentheses. So we're going to do 3 plus 6 inside because that's, the parentheses that we have. So 3 plus 6 is going to be equal to 9. Again, apologies. Okay, and now we're just left with 9 divided by 3 plus 3. Okay, so once again, hopefully you guys are not thinking about doing the 3 plus 3 first because division should take priority, right? So 9 divided by 3, and we're going to say that this is 9 divided by 3 is equal to 3. And then we still have the plus 3 over here that we never touched. And 3 plus 3 is finally just equal to 6. Okay, so hopefully you guys all arrived at the same conclusion, and this was relatively straightforward given everything that we just discussed. Okay, so we talked about natural numbers as being a set. We talked about integers as being a set. There's also a couple other sets that we should discuss. One of them is rational numbers. So a rational number is going to be any number that can be expressed as a quotient. So quotient implies division. So any number that can be expressed as a quotient of two integers as long as the denominator is not 0. So what do I mean by that? Remember how I just talked about there's two different ways to denote division. There's, the actual division sign, and then there's a fraction. Okay, so what a rational number is basically just, it implies division. So some examples of rational numbers are going to be 1 over 2, right? 99 over 14. We can even make it negative. Negative doesn't matter. It's still a rational number. And any other integer. We can actually take any integer in general and make it a rational number because, let's say, for example, we take the number 6. Well, 6 is the same as 6 over 1, right? Any number divided by 1 just gives you back the same number, right? So because we have 6 over 1, we see we have a divisor here. And so any integer is actually secretly a rational number, okay? We can also, on top of these examples, we can also add in one other example, which is numbers that repeat. So, decimals, for example, that repeat in a specific pattern. So, for example, say we have 0.333, so on and so forth, and you denote repeating numbers with a bar over the number, right? So 0.333 is the same thing as 0.3, the 1 bar. And finally, that's just the same thing as 1/3, right? So as we can see here, we do have a divisor. And as long as we have the repeating, the repeating decimals that go in a pattern, then it is a rational number. So when we have numbers that don't fall into that type of general scheme, what we call those are irrational numbers. I'm not going to touch on them too heavily now because there's really only one irrational number that you guys are probably super familiar with, and that irrational number is pi. Everybody knows pi, right? So pi is equal to 3.14159, and then, it just goes on and on and on. I believe the next couple digits are 926, but it doesn't matter. So it just keeps on going. So what's the difference between this and what we just talked about, with 1/3? Well, in the example of 1/3, again, we know that it's just going to be 3 repeating, right? We have a pattern here. We can establish that we know that the next number is going to be 3, or the next digit is going to be 3, 3, 3, 3, so on and so forth. We actually don't have that ability with pi. We don't, it's almost random, right? So we start with a 3, then we have a 1, a 4, a 1, a 5, right? And it just goes on and on and on forever, but there's no specific pattern, which basically means that pi is irrational. Okay? All right. So what we now have rational and irrational as far as sets are concerned. So the biggest set that we're going to concern ourselves with in algebra in this class is the set of real numbers. And what real numbers are, as denoted by this fancy R, real numbers are just all possible rational and irrational numbers. So whenever you think about any fraction, any negative number, whenever you think about pi, or I'll throw in one other irrational number, which we'll talk about later, but another example of an irrational number is square root of 2. So whenever you think about any of these numbers, they are all real numbers. Okay, so what we do when we're talking about real numbers, as far as a visual representation of real numbers, is we talk about the real number line. So the real number line, which we can start it anywhere, but more often than not, you're going to see it start at 0. And obviously it goes on 0, 1, 2 to infinity, right? And then obviously there's also the -1, the -2, and that also goes on to negative infinity. The reason that this is so helpful is because we can actually describe solutions or different events with the real number line. So what do I necessarily mean by this? Well, say I wanted to say the solution to a particular equation is all the numbers between 0 and 2, right? So I'm going to clean this up a bit. Okay, so all the numbers between 0 and 2 just happens to be the solution to one of the examples that I'm doing. So what we can do is if we want a visual representation, well, we can start it at 0, right? And we only necessarily care that it goes all the way up to 2. And what we do is if we want to include 0 and 2, if 0 and 2 are solutions, we draw circles over them and we fill them in as such. And obviously, like I just said, all the numbers between 0 and 2 happen to be solutions. So we just kind of fill in the space between 0 and 2, and that would be our solution set. And we would write this as a bracket, 0, 2, and another bracket. The bracket indicates that we are including the number, the ending number here. So the ending number on the left side is 0, the ending number on the right side is 2, and we want to include those. So because again, we're denoting it by the filled in dot, right? So because we're including them, we use brackets. Now, say I said, for example, that the solution to one of the examples that we're doing is from 0 to 2, but 0 and 2 are not solutions to the equation that we just did. Well, in that case, what we would do is we use parentheses. And we say, okay, well, it's still the interval from 0 to 2, but we don't want to include the endpoints. So what we would do is, again, visual representation, right? From 0 to 2. And we know that the solution is all the numbers between 0 and 2, but it's not including 0 and 2. So what you would do is you would just draw an empty circle or an open dot over 0 and 2. Now, depending on your textbook, I do just want to make a quick note of this. These are equivalent, what I'm about to do. So as far as this above one and what I'm about to write in blue, these are entirely equivalent. So say we had, again, same thing from 0 to 2, and we wanted all the numbers between 0 and 2, but we didn't want 0 and 2. We don't want the endpoints. You could just draw parentheses directly onto the real number line. Okay. And again, that should kind of match up with your interval here, right? So if we're talking about all the numbers from 0 to 2, not including the endpoints, we use parentheses. You can use on your real number line either open dots or parentheses again, just to kind of reinforce that. Both of these are acceptable. Different textbooks will have different things. I know that I personally was taught to use the open and the closed dots. Whichever one that you guys choose to use is entirely up to you. Okay, so let me go ahead and put an example up, and I'll give you guys a couple seconds to try to figure it out, right? Okay, so I'm going to write it out here. Say your solution set, so the numbers that we care about, the numbers that I want you to plot on your real number line are all the numbers between -1 to 1, including 1, and all the numbers after 2, not including. Okay, so I'm going to leave this up on the screen here. I'll give you guys a couple seconds here if you want to pause the video to go ahead and give this a shot and see if you can figure out how to plot this on a real number line. And then we will go ahead and go over it in just a second here. Okay, so hopefully all you guys got it. So for those of you who just want to see how it's done, what we're doing here is, again, we're drawing our real number line, right? And we're trying to describe this event here. All the numbers between -1 to 1, including 1, but not including -1, right? Or else I would have said so. And all the numbers after 2, but not including 2. Okay, so let's break it up into pieces. First, we have the first piece of all the numbers between -1 to 1, right? So we have -1 We'll say that this is 0 here. We don't much care about it, but that's okay. And then this right here would be 1, right? So all the numbers between -1 to 1. So we know that we're going to fill this space in. Okay. Now, what are we doing at the endpoints? Well, we know that we are including 1, and by default, we're not including -1, right? So what I'm going to do is I'm going to use the dot notation. Again, you guys can feel free to use parentheses and brackets if you'd like, but dot notation it is for me. So we are not including -1. So we're just going to draw an open circle over -1, but we are including 1. So we draw a circle or a dot to fill in over 1, right? Okay, so now we also have the next piece of all the numbers after 2, but not including 2. So we have -1, 0, 1. We have 2. And we want all of the numbers after 2, but not including 2. Okay, well, that's totally acceptable. So what we're going to do is we're just going to fill in all the numbers that essentially go on to 2. And it's implied that this goes on to infinity. So, this is a totally acceptable rendition of how to draw the number line. And we want to not include 2, right? So once again, what we're doing is we're drawing just an empty dot or an empty circle over 2 because we are not including 2, okay? And last but not least, if you want to write this in a particular notation, well, the notation that we're going to use is what is known as interval notation. And, well, what are intervals? Well, intervals are, from one number to the next, right? If we're talking about all the possible numbers that satisfy a particular equation, then the interval notation is by far the easiest way to describe it. So interval notation says, okay, well, we want -1 to 1. And now remember, since we're not including -1, we're going to start with a parentheses, right? So starting with the parentheses, and then we have -1 is our endpoint. And for the record, I had this as some people were confused in prior classes. I just want to get this straight. When you guys are writing your answer in interval notation, you're always going to start with your lowest possible value first, right? So in this case, -1 is the least, it's the smallest number that we care about, right? So we're going to start from -1 and then continue to describe it, essentially reading from left to right, okay? So we have parentheses because, again, it's open circle. We're not including -1. And it's from -1 to 1. This is our next endpoint. But we are including 1, right? So what we're going to do is, again, we use brackets to denote that we are including that number. Now, we also have the next piece, which is all the numbers after 2, but not including 2. So if we're not including 2, we have to use the parentheses. And we know that if it's going on and on and on forever, it's going to infinity, right? So we draw a little infinity sign. Now, this is also a common mistake that I see. When you guys are doing this, when you guys ever use infinity or negative infinity, which we can touch on in a bit, you are always going to use a parentheses. The reason is because you can never actually be at infinity, right? Infinity goes on and on and on forever. Bracket is supposed to denote when you're actually at that number, when you've stopped there. So we've stopped here at 1. So that means that we're going to use the bracket here. We haven't stopped at infinity because you can't stop at infinity. It just continues to go, right? So what you're always going to do is you're always going to use the parentheses when you're talking about infinity or negative infinity. Okay, so now we have these two pieces. We have these two different intervals. But really, it's one interval, right? Because this is all one answer to what we were trying to describe before. So what we do is we draw this kind of U-looking thing. And what the U is it stands for union. A union basically means and. So when you think of these two being put together, you think, okay, well, I have this piece and this piece, so it is all my final answer, which try to get in the habit of boxing your answers. Okay. So hopefully that made sense to you guys. And I will go ahead and try to give you one more example here just to really hammer in the idea of interval notation and trying to plot on the real number line. Okay, so just give me 1 second. Okay, So let's say we want all the numbers to -3, and we want not including. Okay. So say this came up and on your exam or on your homework or what have you, and you had to try to plot this one out. So you have all the numbers to -3, not including -3, and then all the numbers after it. So go ahead and I will give you guys again another couple seconds, see if you guys can figure this one out. Okay, so we go back to the real number line, right? So we're on the real number line, and the reason that we're going to start here with -3 in the middle is because -3 is like the only number that we care about in this instance, right? It's the only number that's actually being described. So we want all the numbers that go to -3, not including -3, and then all the numbers that are after it. Okay, so we know that going from left to right, we have all of the negative numbers that go to -3, and then we don't want to include -3, so we draw an open circle, and then we have all the numbers that follow -3, so once again, we're going to shade in that part of the number line. So as you can see, almost all of the number line here is being covered or being shaded, with the only exception being -3. Now, how would we write this with interval notation? Well, we say, okay, we're starting technically from -infinity, right? If we're going all the way to the left and we're counting all the numbers to the left of -3, then that is going, -4, -5, -6, so on and so forth, and it's going on forever, right? So -infinity. And remember what I said, when you're dealing with infinities, you're always going to start with a parentheses if you're dealing with when you're dealing with infinities in general, be it negative or positive. So we have -infinity, and we know that it goes to -3. And remember, we're not including -3 here, thus the open circle, so parentheses. Then we have the next piece, right? We have an and, right? All the numbers that follow -3. So we have then after -3, -2, -1, 0, so on and so forth, and it goes on to positive infinity, right? So we have to start from the same place that we ended before, right? We ended at -3, but see that this next piece, the after the and, is taking place starting at the -3, right? So we have infinity to -3, and then starting here at -3 again, this goes on to infinity. And we have a parentheses because, again, infinity, you have parentheses. And last but not least, the piece that we're missing here is just the union, because we're saying it's this interval here and this interval as well. Okay, so hopefully that all made sense. Again, come prepared with questions if that didn't really get through. We're going to just do one or two more topics here, and then we will call it a day, okay? All right. So with real numbers, there's a couple properties of real numbers that we have to discuss kind of at length. So I'm just going to get rid of these off the screen here. Okay. So the first property of real numbers that we should talk about is trichotomy. And I will go ahead and write that one out for you. Trichotomy. Okay. And what trichotomy is it basically says that one of the following statements is always going to be true if you're considering two numbers. Either those two numbers are going to be equal to each other, one number is going to be less than the other, or that same number is going to be greater than the other number. So what do I mean by that? Okay, say we're considering 3 and 4, right? One of the following statements is going to be true. Either 3 is equal to 4, 3 is less than 4, or 3 is greater than 4. So we have three different statements, and only one of them can be true. And this is trichotomy stands for any two real numbers. So whenever you pick any two real numbers, only one of the following things is going to be true. Okay, so very obviously 3 is not equal to 4. We know that 4 is bigger than 3, so that's out. So that means that our correct answer here, or our correct interpretation, is 3 is less than 4. So again, trichotomy just says that only one of these is going to be true whenever you consider any two real numbers. Okay, that one's pretty easy. It's pretty intuitive. You've probably already considered that at some point, even though you might not have known the name trichotomy. Okay, another one that we have to talk about is transitivity, and I will go ahead and write this one out as well. Okay, so what transitivity is it basically says, okay, say we're considering 3 numbers, right? And we don't know necessarily what those numbers are. So we'll just call them A, B, and C. Okay, again, remember, we're talking about variables, right? If we don't know what the numbers are, we use variables or letters to represent them. So we're now considering A, B, and C. Okay, so regarding A, B, and C, if, and again, big if, so if A is equal to B, and also if B is equal to C, then we know that A should be equal to C. So what does a visual representation of this look like? Well, again, if we don't necessarily know what the number is, let's go ahead and just pick one at random, right? Let's say A is equal to 4, for example. So I'm just going to go ahead and scroll down here. So let's go ahead and say, all right, let A equal 4. Okay, so we know from above, if A is equal to B and B is equal to C, then A should be equal to C, right? Well, if A is 4 and A is equal to B, then that means that, well, B should also be 4, right? Because B is equal to A. Okay, and then also we know that B is equal to C, right? So if B is 4, then that means C is equal to 4, right? And then last step that we know is that if A is equal to 4 and A is equal to B, B is equal to 4, C is equal to 4, well then finally A is equal to C because 4 is equal to 4. It's just a pretty simple way of just, saying if you have a middleman and they're all equal to each other, then the two endpoints are also going to be equal to each other. Okay, so let me go ahead and clean up the board here. All right. Now we can also say transitivity applies not just to equivalencies, but also to inequalities. So the next step that we can take here logically is, okay, well, let me scroll up. So we have if A, and we'll say is less than B in this case, right? And B is less than C. So if A is less than B and B is less than C, then what we know then is that A is also going to be less than C. And let's look at a real example of this again. We're just going to use really basic numbers. So say A is 3, B is 4, C is 5. Well, and I'll write that out over here. So A is 3, B is 4, C is 5. Okay, so this should logically make sense to you, right? If A is less than B, so we know that 3 is going to be less than 4, and B is less than C, we know 4 is less than 5, then we know by default that A should be less than C, which again should hold, right? 3 is going to be less than 5. And that's it. That's all transitivity really is in a nutshell for equivalencies and also inequalities. Okay, so I think that this is a good place to stop. I've been kind of going on for a little bit. Feels like a natural stopping point. We'll pick this back up with the next lecture, which should definitely go a lot more smoothly because I will have the tablet at my disposal, which will have the stylus, and again, it'll make things a lot more clean and apparent. So thanks for bearing with me for the first lecture. I will go ahead and post homework, and yeah, so you guys can go ahead and get started on that and have questions prepared for Friday. Okay. All right. Thank you guys and enjoy the rest of your night.